let's go ahead and learn about and carry out a one-sample t-test. Chapter 15 presented the large sample test of the mean. The one-sample t-test hypothesis pairs are exactly the same as for the large sample test of the mean. Just as does the large sample test of the mean, the one-sample t-test examines whether the mean in a random sample differs significantly, which is to say, by more than would be expected by chance alone from some stated value. One may not use the large sample test when n is less than 100, and a major reason for this is that the estimate of the standard error of the mean may not be sufficiently accurate. Here are the hypothesis pair. Here's the hypothesis pair for where the pair is non-directional and therefore the test is two-tailed. I'm not listing the directional pairs, but when the pair is directional, you use a one-tailed test. And again, the directional pairs are identical to the directional pairs for the large sample test of the mean. The one-sample t-test does assume that the population from which the random sample is selected is normally distributed. However, it's robust to this assumption. Pragmatically, it's accurate in the same situations as is the 95% confidence interval for the mean calculated with the t-test. So, if you have sample size that's 20 or greater and your sample does not have extreme skew, as demonstrated in the figures in Chapter 5, you're going to get sufficiently accurate results. If you have a sample size of 100 or greater, you're going to get accurate results even when skew is extreme. Just as is the case for confidence intervals, when sample size is greater than 100, tests based on the t-test are used much more often than are those based on the normal distribution. So even when sample size is greater than 100, I recommend using the one-sample test rather than the large sample test. The one-sample test is used much more often and much more commonly. Frankly, the large sample test and the confidence intervals based on the normal distribution, their primary use is in teaching concepts in statistics, but in practice, t-test based formulas are used much more often. We will shortly carry out an example using a non-directional hypothesis pair and thus a two-tailed test. So here is the decision rule for that situation. Fail to reject the null if the absolute value of the obtained t is less than the value of t in the t-distribution table. Reject the null if the absolute value of the obtained t is greater than or equal to the value of t in the t-distribution table. Now you can see that these formulas for the t-test are just the same as the formulas for the large sample test. We're computing t's rather than z's, and perhaps you recall we used approximately equal symbols rather than equal symbols in the normal distribution-based formula. Because when you calculate using an estimate of a standard deviation formally, you're calculating a t, not a z. So these are the same formulas that you've already used. And in words, you subtract the value stated in the null from the sample mean and divide by the estimate of the standard error of the mean to carry out a t-test. So here is our working example in a large state that borders the state where you work. All clients in that state receive mental health services, take a social functioning scale or measure. The mean score of that very large group of clients is 50 points. Now, you administer the scale at the clinic where you work. you administer to 25 clients. The mean score of those 25 clients is 45, and the standard deviation is 15. And I've just corrected the slide and written in that 45 is indeed the mean. Further in your sample, you see a strong negative skew. Now, just as is so for confidence intervals based on the t-distribution, the one-sample t-test is basically robust to non-normality. So our guideline was if n was greater than 20 and there was not extreme skew, you could carry out the test and your results will be sufficiently accurate. So n is indeed greater than 20. The skew is strong rather than extreme. So therefore we're going to get sufficiently accurate results. The first step in our hypothesis testing model is to state a hypothesis pair. So our null states that the population mean at your clinic is 50. The alternative states that that mean is not 50. The second step is to choose a significance level, and we'll choose the most commonly used significance level, the 0.05 level. The third step is to carry out the calculation, and the first step in that calculation is plugging our formula in for the estimate of the standard error of the mean. So we take the sample standard deviation of 15, we divide by the square root of the sample size, and the estimate of the standard error of the mean is 3. So then we carry out our calculation. We take the study sample mean, we subtract the value stated in the null, we divide by the estimate of the standard error of the mean, which is to say the estimate of the standard deviation of the sampling distribution, and our obtained t computes to minus 1.67. So our final step is to make a decision regarding the hypothesis pair. In order to do that, we need to calculate our degrees of freedom, and we have again 24 degrees of freedom. With 24 degrees of freedom, we use the column that lists alpha equals 0.05, and it's the same column that we use for the 95% confidence intervals. So we get the same value actually that we used in the confidence interval example, 2.064. So now we need to apply our decision rule. The absolute value of our obtained t, which is to say the absolute value of minus 1.67, is 1.67. 1.67 is less than the t in the table, this being the critical value of t. This being the case, our decision is to fail to reject the null. And we are going to reject the alternative. So in our situation, we cannot conclude that the population mean in your clinic differs significantly from 50. The difference that we see in your random sample is plausibly due simply to chance, the luck of the draw. So here is a visual of the result. Your study sample mean is 1.67 standard deviations below the mean. It is not sufficiently extreme to reject the null. The rejection regions are beginning 2.064 standard deviations from the value stated in the null. So you fail to reject the null. Now it might be useful to get an example of a directional hypothesis pair. So suppose that your strong expectation was that social functioning at your clinic was at a lower level than that in the neighboring state. If that expectation was sufficiently strong, a directional pair would be a good choice, and it would be the alternative hypothesis that would carry the direction of expectations. So the alternative is that the mean in the population at your clinic is less than 50. Here is the decision rule of the alternative states less than for the one sample t-test, and that is fail to reject the null if the obtained t is greater than the negative of the t in the t-distribution table. Reject the null if the obtained t is less than or equal to the negative of the t in the t-distribution table. So, what do I mean by the negative of the t in the table? It is the case that all of the values of t in the table are positive values. So the negative is simply the negative value that is, so to speak, the opposite of the positive. So for instance, the negative of 1.711 is minus 1.711. And indeed, we have 24 degrees of freedom, and we have an alpha level continuing to be 0.05, and the difference in terms of our referencing of the table is that we're on the far right side of the table in the text, and we're under the columns for the one-tailed test rather than for the two-tailed test. The negative of the t in the table is minus 1.711 minus 1.67. Our obtained t is greater than is minus 1.711. It's greater than the t in the table, and therefore we fail to reject. That is to say, we accept the null. And in this example, we just miss rejecting the null. So here is a visual of our result, and since we have a one-tailed test, the entire rejection region is in one tail. I mean, it is indeed in the tail that is in the direction stated in the alternative, the direction of our expectation. So thinking back, for our two-tailed test, we had to go out just a little bit more than 2 standard deviations to reach the rejection region in the negative tail. But the rejection region in the one-tailed test is larger, and it begins closer to the value stated in the null. So it begins 1.711 standard deviations below the mean. And our result was minus 1.67, so we just missed rejecting the null here. But this does demonstrate, again, when the result is in the expected direction, then it is indeed easier to reject the null with the directional hypothesis pair and therefore the one-tailed test. Well, that concludes this video. We didn't go through all of the different decision rules and contingencies, but you can take a look in the chapter, which gives you some additional information. Chapter 18 is our next video, and it is going to talk about the independent samples and dependent samples t-tests, both of which involve 2 samples rather than just a single one.